Hey Blackie, you want to come outside with me and help me record a special episode of Geo-Files? Blackie? I think you want to stay here. Hello everybody, welcome to the Geo-Files. I'm going to digress from more technical stuff this one. Think of this as a special episode. I'm going to talk about a lot of the rocks here that I have on display, the bigger ones, where they came from, their origins, stuff like that. Nothing too complex. And if I can remember their location, I will include maps of where they came from. But first, this person did not ask me to do this, but somebody designed this t-shirt for me. It is a Bedrock Geologic map of North America. It is based off of a USGS map, and it is actually, it came out a lot better than I thought it would. I mean, it'd be cool if it was a little bigger, but still, that is 1,000 times better than I thought it would. I will link the store below if you care to get stuff yourself. No pressure. We are going to start out here, but I may move it into the lab. There's rocks in there I would like to show you. But this, I love this. This was collected, well, there's like 3 Presque Isles in Michigan, and 2 of them are in the Upper Peninsula. You're not allowed to collect in the park. This wasn't actually in the park. This was pulled several, I think probably 3 to 5 meters offshore, so it's technically outside the park. But these are exposed inside the park. This is a smaller one. Some of the bigger ones are like this. And you may be looking at this and be going, oh, that's a fossil. Oh, that's a stromatolite. Something like that. It is Precambrian, so it's not a macrofossil. Matter of fact, this isn't a fossil at all. I apologize for the bird poop. This is an outside rock. This thing is actually pretty dense. The rock surrounding this, the host rock, as you can tell by looking at this, is a brown to black shale. It is from the Nonsuch Formation. I have talked about this formation before. It is the one formation of the Oronto group and Jacobsville group that I will not be touching when I do reclassification of nomenclature and detrital zircon studies. This not at all. I'll leave that up for somebody else. The stratigraphy of this is really complex. It's a series of terrestrial lacustrine deposits, some river deposits as well. But as you look at this weird shape and you're like, how could that not be a fossil, Steve? Well, it's not. There's some broken open. You see them, that's actually carbonate. This thing's pretty heavy for as small as it is, because it's not made of shale. It's within the shale. You can get carbonates within plastic rocks. It's nothing unusual. But what is how this formed. Okay? Now, I've talked about the Mid-Continental Rift before, and I've taken you to places like the Keweenaw Fault, and that was a recent video. The Mid-Continent Rift is about a 1.1 billion with B-year-old rift that failed. It tried to split North America in the area of Lake Superior. It extends further than that underground, but talk for another time, which is kind of funny because 2.5 billion years ago, the continent did successfully rift there, and what used to be attached is probably now part of South Africa right now, or Wyoming. But back to this. Why am I telling you about the Mid-Continental Rift? Because this is tectonically induced. As that rift, and I've done this before, cross-sectional view, as that rift stopped spewing volcanics, the continental crust stopped extending, that basin stopped forming, and the volcanics emptied, you started to get clastic shed in to that basin. Well, this rock isn't a clastic. The Nonsuch is a clastic. This is a carbonate. However, as that came in, the region was still tectonically active. That magma chamber had stopped venting lava. So it subsided. As these clastics came in, there would still be tectonic movement. Now this is pre-reversal of the normal faults that bound the rift. So as these earthquakes would happen, you would get carbonate muds on top of mud. All right? You know, shale, carbonate shale, whatever, in these lakes. An earthquake would happen, and it would roll downhill and form these balls. This is one of those balls. This one just happens to be carbonate dominated. There are some that are a mix of carbonate and shale. If you break them open, you can see both of them. I don't want to break this one open. That's not going to happen. I've already talked about this in a recent video. This is Frida with ripple marks, so we're not going to talk about that again. We are going to talk about other Mid-Continental Rift rocks before I get out of the Mid-Continental Rift. This. Okay. We were at Seneca #1 mine for mineral days a couple of weeks ago now. And we were looking for copper. We did find some native copper. Native copper, I mean, the Keweenaw Peninsula is a place for copper in the world. There's no other better copper deposits known to man than there are there. But this is the basalt. This would have been deposited while the rift was still rifting. And you can see the cool weather patterns in here and some other things. This is a basalt. See how it's reddish in color? And then it turns purplish gray here. But it's ambogoidal up here. That means that's what these little holes are. These were, as this is spewed up on the surface, these would contain gases. Those gases would release, later solidify and fill with minerals. Some parts are not ambogoidal. Now this, good plagioclase development right there. And you got some calcite, which formed even later. And there is not a lot of epidote in this sample. The area does have a lot of basalt with epidote in it. So I just thought I'd show you that beautiful big one real quick. This is also Mid-Continental Rift basalt. It's not as well indurated or as stable. You see these huge, just move it in the light for these huge reflections. Those are massive mafic crystals. And you can see it weathers pretty quickly. This big piece is already breaking. This is from Canada. I forget the exact outcrop, but it's on the east shore of Lake Superior. It's taken from Trans-Canada 17. But I just show this one because of how large those mafic minerals are. And they're not biotite or musket, they're not micas. Going back a little further in time, 1.8 billion with a B years ago, we have banded iron formation. I believe this is from the Jackson mine. It was a gift. But what you can see about this, notice the shiny gray, that gleaming part, that's hematite. Okay, this particular specimen does not have a lot of magnetite in it. Magnetite can be part of it. Not this one. That purple and that red is what people call jasper. What it really is, it's just red chert. This is the only sedimentary rock that Earth no longer makes and hasn't for 800 million years or more. They're really common in the Precambrian up until about 1.85 billion years ago. I don't know off the top of my head exactly how old this one is. Probably somewhere between 1.7 and 1.9 billion with a B, so about 1.8. But after 1.85 billion years ago, the banded iron formations were still being formed by greatly reduced rates, and that seems kind of odd to us. Today, we figure they don't form, these are sedimentary, like I mentioned, they don't form because our ocean and atmospheric chemistry is no longer conducive to their formation, and the type of microorganisms that may have been responsible for depositing them, at least in part, no longer exist. So that could be a 2, but there's something that may have happened at 1.85 billion years ago to pull back on their formation a lot. I have shown this to you guys many, many times, many different examples, but what deposited this was probably responsible, at least in part, for the demise of the banded iron formations. 1.850 billion with a B, or 1,850 million years ago, plus or minus only a million years, something hit the Earth. An asteroid, comet, I don't know, that was larger than the KPA-1 that famously killed off the dinosaurs, or suspected to, at least most of the non-avian ones. Smacked into Earth in Sudbury, Ontario. This is not from Sudbury. This is from Thunder Bay, Ontario, and I forget the exact distance off the top of my head. It will be put down below in scrolling text for you. But this is ejecta from that impact. And you can see it contains a lot of conglomeratic or rounded stuff with ash in it and whatnot. This is a polished surface. right? And this is the unpolished surface. This impact probably had global ramifications for microscopic life, which is all that was around at the time. The Precambrian likely also has mass extinction events, just like the Phanerozoic. And this impact was probably the cause of one of them. And it probably is no coincidence that after this hit, that banded iron formation started to curtail and drop off. We still argue about what formed them. Some people are in a camp of totally inorganic. Some people are in a camp of totally organic. I'm talking about banded iron formations here a bit. But reality is it's likely a mixture of the two. And there is strong evidence for organic formation. And the fact that after this event, they drop off a lot also supports that greatly. Perhaps one of my favorite pieces is this. This is seam agate on the Gunflint formation. We are still at about 1.8 billion years. As a matter of fact, the sub-area impact occurred while this was getting deposited, the Gunflint, so we have a firm age for it. But you notice there's red jasper on this and that beautiful white quartz in there. Look at that, I love that. And this is an iron carbonate, the Gunflint, and it is actually a very diverse formation. People don't give it the proper credit, but this was collected in 2012 on an ILSG meeting. We were on Trans-Canada 17 and they were doing road work at the time. We went down there and we found a bunch of these. So we picked them up and we took them home. The Gunflint, you can see the laminations within it. There was a piece above this. I have smaller pieces of this. This is one of the sources of Lake Superior agate. It's not the only source, but it is one of them. So I just think that's really nifty and cool to show everybody. And within this formation as well, there's amethyst. This is not the best sample. The crystals are beautifully well developed though. It's just not a big booming crystals of amethyst. This also came from the Gunflint. This was also collected on Trans-Canada 17. Sarah went inside, I think it was last year we were there? Yeah, had to be last year. There was a cavern inside one of the road cuts and she crawls in there and starts pulling these things out. So you get amethyst in this as well. Bugs are starting to get bitey. Anyway, let's move away from Lake Superior into Wisconsin for a bit. I've shown you guys this before and I have really good samples of this, but this is purple Baraboo quartzite. I've shown you this before, so I'm not going to go into great detail about it. Plus I have probably 5 to 10 videos on the Baraboo area. But this piece I keep out. It is a quartz arenite. It's quartz mostly. The purple is caused by iron. I've talked about this before. And these black spots are hematite. And they sometimes form along bedding planes. This is a low-grade metamorphic rock. It is from southern Wisconsin. Deposition I've mentioned in other videos before. After deposition, it was buried, compressed, lithified, and metamorphosed in an orogeny, forming the Baraboo syncline. Let's roll the clock back, way back for a little bit here. This and this, I can talk about them together, are both Archean in age. And they are both from the north shore of Lake Superior. I forget the exact outcrops, where we got them from. I would have to look it up. But I do remember them being Archean. What you have here is you have a look at how coarse these crystals are. You don't even need a hand lens to identify the minerals in here. You see a lot of dark mafic, a lot of light felsic minerals, to include quartz. This is a granitic rock, but it is foliated. But that foliation is more characteristic of foliation formed as the magma cools. It's plastic for a while, formed before it becomes hard solid. This type of foliation forms more of when it's still plastic and then it cools and locks it and the placement gets hard. This is metamorphic foliation. This type of foliation is caused by metamorphism of, in this case, an igneous plutonic rock. And you can see the darker mafic minerals and the lighter felsic minerals. There's quartz in this. doesn't have the detailed, large crystals that this specimen has. They're a lot finer on here, but this does have this cool later intrusion here of a different rock. This is called a syenite, and that was igneous, and it intruded into this rock. After this went through becoming a magma to a granite and getting deformed to a gneiss. You can even see a little baked area right there, probably for hydrothermal alteration. So I like that one too. And I think that's it. I'm going to show you guys these for right now. So don't have the time to go through every one of these right now. Okay, so we are in the shed, the lab. Not sorry for the mess. A lot of papers, references, things like that. Oh, I was looking for that the other day. I thought it might be nice to give you a different angle instead of the dry erase board that you're always seeing in the background. So, let me get you a couple rocks here. Don't worry, I'm not going to show you too many more. This is going to be pretty long as it is. And I always say that, and then I'm going to show you a ton more. This is from the Randville Formation. It was gotten from Iron County in the Upper Peninsula and during an ILSG meeting, so we had access and we were able to take samples. And they call this a breccia, but it doesn't really look like a breccia to me. It's near the top of the Randville. This is a carbonate. It's stratigraphically equivalent to the Kona and the Gordon Lake in Ontario. But in Ontario, the Gordon Lake is more of a clastic sediment. The Randville and Kona are more carbonates. And a lot of these Precambrian carbonates are very salacious. That's not very common in the Phanerozoic oak, but it is in the Precambrian. And these look to me more like pebbles in place and elongated, the kind of stuff you would get from sorting of a river system moving across a carbonate plane. You can get carbonates deposited as grains. I've talked about this before, and this may be one of those situations where that was the case, that these little things were actually derived from older Randville and redeposited. They follow bedding pretty well. There's a definite class orientation, but I have not studied it in any great detail other than compositionally. So that's just a working hypothesis, if you will. I could be totally wrong. Okay, I've shown you guys this in a recent video. It's a slice of Mississauga Formation, Precambrian, Huronian supergroup, pre-GOE. So there was no free oxygen in the atmosphere when this was deposited. So you get a lot of minerals that like to form in a reducing environment instead of an oxidizing. We don't have red beds for this stuff. They did not exist then. This is mined for uranium because there's uraninite, is that how you pronounce it, in here. What we call pitch blende. And there's pyrite in it. Things that are not very stable in an oxidizing environment, but very stable in a reducing one. So this was only a few million years before free oxygen started getting pumped into the atmosphere. I do have other rocks from impact events, not just Precambrian ones. This is from Indiana, not that far from me. It is from something called the Kenton Structure. And there's a lot of these in the Midwest. There's a couple more in Illinois, like the Glassford and the Des Plaines disturbance. So the Des Plaines disturbance is covered by something like 80 feet, but unlike the ejecta that I showed you from the Sudbury impact, I'll show you something different here. This is what we call a Shatter Cone, and this is in the Silurian deposits within Kentland. We do not have an age for this. Let me do a quick explanation of what is going on at Kentland. This is not to scale. These do not depict the actual units in the ground. The black are false. This is a cross section. This would have been your surface. So your impact would have come in this way, hit, and then kick stuff out. So you would have had your impactor coming in like this, and then kicking your ejecta out. And that would have formed all these black lines, false, normal, reversed, strike, slip combos. It's a juxtaposition of just almost randomness that's really hard to decipher. So I just added 3 geologic units for relative reference, with the thinnest being in the middle, showing you how the deformation occurs. There's no particular age or anything like that here. Like I said, this is not Kentland per se. This is the situation going on. And a lot of these Midwestern, in Illinois, Iowa, Indiana, impacts were not originally recognized as impacts. There was something called crypto-volcanic structures originally, because what we thought had happened, so you get a rise in the middle, like you would from an impact. We have good understanding of impact mechanics now. You get that middle point that rises up. And so a lot of people thought magma was trying to punch through underneath and failed, and this is the remnant of that, or that it gassed out or whatever, but no one has ever found any evidence of volcanism. And you're not going to find any direct evidence of an impactor at Kentland or a lot of these other Midwestern craters either. Why is that? Well, it's not because it didn't happen. It's because significant erosion has subsequently occurred. That whole top part of the impact, the crater rim, the ejecta, all long gone, all eroded so long ago. Now, within Kentland, though, there are the youngest deposits that are Paleozoic. I'm not going to attach it to any of these units, but they're Pennsylvanian, symbol for Pennsylvanian. And the rocks in the middle vary in age, and they're exposed presently. I think the oldest are young Ordovician rocks. So we have that. So you're like, oh, well, when does this occur? Well, we have Pennsylvanian deposits that were deformed because of this impact. So it's Pennsylvanian, right? No, it's not how that works, because we're missing this whole part. And it does have on it modern glacial deposits. These hatched lined glacial deposits are Quaternary in age. That's a symbol for Quaternary. So we have a huge gap of missing time in here. So we do have a gap here of roughly 300 million years. It's a little less than that. Well, is there any way to date this thing? When you have this much missing, and you have no impactor to date, or ejecta to date, or none of that, it becomes problematic. But the best date obtained so far is based off, honestly, secondary evidence, not primary, because you can't directly date any of it. It's Cretaceous. So it's about 90 million years old. And there's a huge margin of error attached to that, but whatever. So that's a quick explanation of why these things are so complex and why they kind of fool people as to what they were, because there's no evidence, surface evidence of an impact. But you know, there's no evidence of cryptovolcanic explosions from underneath either. So the best explanation is that this is an impact. Shatter cones. There are structures similar to these, but they are not related to these, and sometimes it's hard to tell. But in an environment like I've just demonstrated on the board, if you see these, heavily faulted area, disjointed beds, just a stratigraphic nightmare, shatter cones are conclusive evidence of an impact. They only form from shock metamorphism, as you could call it. So something comes in, fast, hard, hits the rock, shatters it, and then it kind of reforms real quick. And it creates these cone structures, shatter cones. This is from the Silurian carbonates. So I just thought I'd show you that one. And real quick on that back shelf, I'm going to show these to you guys because you love them and I love them too. And you never get sick of seeing them, but I have to turn the lights off for it. And I'm going to talk about them real quick. It's dark in here. Long wave UV. You can't see much. Can't see much. Let me get... So you have these rocks up here I'm looking at. There they are. The Uperlites. The origin of these are the Coldwell Complex mostly. Ontario off the northeast end of Lake Superior. Some of them, and I have one that may be from further away, like Greenland. The orange fluorescence here is caused by the mineral Sodalite. And that is common in a failed mid-continental rift in Greenland as well. I have some actual native sodalite here. See if you can see it. I crank it up a bit. And I've shown you this before. See, even that fluoresces orange, even though in visible light it's blue. I'm going to turn the lights back on here for you. Talk about it a little more. This doesn't glow very well right here. It does to the eye. It's a little better to the eye. But that was pulled from outcrop in a vein on Trans-Canada 17. The Coldwell Complex is Mid-Continental rift rock. Other than that orange color, the Uperlites are not that spectacular. They are granitic rocks like this one, but this one does not fluoresce. Why not? Most granitic rocks, what people think as granites, have quartz in them. Actual true granites have quartz in them and above 20% by mass/volume. Uperlites, on the other hand, some of them look like they're granites. They are plutonic rocks, they are not granites, but they cannot be granites because they have no quartz in them. They have sodalite. Sodalite is what we call a feldspathoid. If we were to classify this, we'd have to use the bottom half of the QAPF diagram, or the FAP part, the fat part, if you will, instead of the QAP or cap part, if you will. So no quartz in this rock, no free SiO2. If you have feldspathoids, they require that quartz to form. So you get no quartz. Not all feldspathoids or foids fluoresce like that. As a matter of fact, there's some plagioclases that will fluoresce a little bit. But the awesome thing about sodalite, and I showed you in the bigger blue chunk, is the fluorescence is a primary property of it. It's not due to activator elements. It's not due to impurities. Most rocks fluoresce because of impurities. That is a physical property of sodalite. So you see that orange with a long wave UV, and that one's on a little towards the shorter end of the long wavelength to get it away from the visible light area. You got sodalite. But it's also present in more mafic looking rocks. This rock's a lot grayer, a lot finer grained. It's still considered plutonic than this one is. And this one's that big one that was glowing like crazy that you saw. So this has a lot of sodalite in it. These were both found on a beach on the Keweenaw Peninsula. Friends of ours have a house and some land there, and on the beach we go and we picked them up. It's not protected or anything like that. It's a couple rocks. People pick these up all the time. And this one, I got this from up higher in the beach. Most people around the lake going like this after night, looking for the stuff that just washed up, and they forget to go a little higher up on the beach, and that's why I stumbled into this big piece. Before I wrap it up, and I've shown this piece off before, I talked about how the Keweenaw Peninsula and the Upper Peninsula of Michigan, it's actually technically an island, is world known for its native copper deposits. And when I mean native copper, I don't mean isolated little flecks here and there, although that does happen. You do have disseminated copper as well. Disseminated copper is actually present on the west end of the UP in the Nonsuch Formation at the White Pines Mine, which was not that much further from that round ball of Nonsuch I showed you. The carbonate round ball in the beginning of the video. But here we're up further. In the old copper mines, they chase down these interflow conglomerates, which I've mentioned before, and we visited the Aloes conglomerate at Delaware Mine, self-guided tour. They find copper. This is native copper. This is a chunk of native copper pulled from the ground. You can even see the clasts that held it into place, the conglomerate clasts. This is common. And many people, when I first posted this, many people were shocked that I had this. And I'm like, this is common. People find stuff like this in metal detectors all the time. I didn't think it was that odd. And you see rock shops selling much bigger pieces than this one. And it dawned on me how rare copper really is outside of the Keweenaw and how unfamiliar people are with it. But this is by no means the biggest piece of copper found. Before I wrap it up, I just want to show you guys this real quick. This is a medium drill bit, 19th century. That would be at the end of a long rod. For those of you that watched the Delaware Mine, you notice that it followed the Aloes conglomerate, which dipped about 24, 25 degrees. And they would have this at the end of a drill, and they would just drill into that rock. We did purchase this at the Delaware Mine, just thought it was really cool. Anyway, that's it. If you have any questions or comments, please leave them below. I hope you enjoyed this, and I hope you learned something. Feel free to leave suggestions for future Geo-Files episodes down below.